Welcome back to Arxflix. Today, we're exploring a pivotal paper in deep learning titled On the Variance of the Adaptive Learning Rate and Beyond. This paper examines why the learning rate warm-up heuristic is so effective and introduces a new optimization algorithm called Rectified RAdam. Let's start by understanding the problem. Traditional adaptive optimization methods like RAdam and Arxflix are widely used. However, they often converge to poor local optima unless a warm-up strategy is employed. The learning rate warm-up involves using a smaller learning rate at the initial stages of training. Here, Figure 1 shows how removing the warm-up stage for training transformers on the Fortin dataset drastically increases the training loss. This phenomenon is also seen in other models, like BERT. The paper's authors delve into the root cause. The variance of the adaptive learning rate is particularly large at the early stages of training. They hypothesize that warm-up effectively reduces this variance, making training more stable. They provide empirical and theoretical evidence to support this hypothesis. Inspired by their analysis, the authors propose Rectified RAdam. This new algorithm rectifies the variance of the adaptive learning rate explicitly. By introducing a term computed using the number of used training samples, RAdam improves both the stability and performance of model training. RAdam was tested across various tasks including image classification, language modeling, and neural machine translation. In all cases, it showed significant improvements over vanilla RAdam. Figure 4 illustrates the performance of RAdam on language modeling tasks using LSTEMs on the 1 billion word dataset. RAdam converges faster and achieves better performance compared to RAdam and SGD. Now, let's dive into the core mathematical insights. The variance of the adaptive learning rate is initially very high due to limited training samples. This can lead to the model getting stuck in bad local optima. By rectifying this variance, RAdam improves stability. Here's the key equation where psi is the adaptive learning rate function and rho is the number of used training samples. The variance decreases as rho increases. Figure 3 shows the gradient distribution during training. Without warm-up, gradients are distorted in the first few steps, trapping the model in bad local optima. The proposed RAdam algorithm doesn't just rectify the variance, but also eliminates the need for manually setting warm-up hyperparameters, making it more user-friendly. Figures 5 and the accompanying table display the performance improvements in image classification tasks on Fortin and ImageNet. RAdam is compared to the traditional warm-up strategy. On neural machine translation tasks, RAdam showed similar or better performance without the need for additional tuning, demonstrating robustness and effectiveness. Figure 7 depicts the performance of RAdam and RAdam with warm-up on the Fortin dataset. RAdam not only shows better accuracy, but is also less sensitive to learning rate changes. To sum up, the paper successfully identifies the high variance of the adaptive learning rate as a critical issue in early-stage training. By proposing RAdam, the authors provide a robust alternative to the warm-up strategy. RAdam not only improves performance, but also simplifies hyperparameter tuning. That's all for today's episode of Arxflix. Check out the paper for more detailed insights and the code available at the provided link. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the latest research. See you next time. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.